So let us continue now the isomerism in complex compounds. You have completed isomerism in coordination number 4, geometrical isomerism in coordination number 4, that is tetrahedral geometry and square cannot be taken. Tetrahedral geometries cannot exhibit geometrical isomerism, we discussed, and only scale penor geometries exhibit geometrical isomerism. Different types under scale penor geometry with monodentate ligands and also bidentate ligands. We thoroughly discussed different models I shown on the board. Next, today we will discuss same geometrical isomerism with coordination number 6 and octahedral geometry. Geometrical isomerism with coordination number 6, octahedral geometry. Geometrical isomerism in octahedral geometry. Octahedral geometry. Now, under this types, let us say, we will take now first with monodentate ligands. With monodentate ligands. Take the first one, Ma6 plus or minus n, Ma5b plus or minus n, no geometrical isomerism. Look here, all the 6 ligands are same or 5 ligands are same. We cannot write any second structure or second geometry for that particular complex. Therefore, in octahedral geometry, all the 6 or 5 ligands are same. Such complex cannot exhibit any geometrical isomerism. So, here no geometrical isomerism. No geometrical isomerism. Coming to the second one, there should be at least 2 ligands different. So, what are the types you see now? Ma4 B2 plus or minus n, Ma4 BC plus or minus n, Ma3 B3 plus or minus n, Ma2 B2 C2 plus or minus n, Ma4 B2, Ma4 BC, Ma3 B3, Ma2 B2 C2. Next, you can also take Ma2 BC DE plus or minus n. Next, Ma B C D E F. So all the 6 ligands are different from each other. All these complexes, all these models exhibit geometrical isomerism. All exhibit geometrical isomerism. Exhibit geometrical isomerism. Let us see one by one all these different types. We will take the real complex. We will discuss how they are exhibiting geometrical isomerism. Take the first one, Ma4 B2 plus or minus n. See, 4 ligands are of one type, 2 ligands are of the other type. So, this we can write, say one complex, whatever you know this, take CO hydroxide taken 4 times, Cl2, Ma4 B2 plus. You can write cis and trans, look the board, octahedral geometry, make octahedral geometry. Right, 2 chloro ligands are writing cis to each other, adjacent. Remaining 4 ligands, So this particular complex we consider what a cis. Cis. Then one more I write trans. We'll keep this particular chloride ligand in the axial position. This you consider as what trans. Cis complex and trans complex, two complexes. That is what these two are geometrical isomers to each other. You can also take next one Ma4B2 I written now. You can take Ma4BC. Keeping the two different ligands, let us consider simply one is chloride, one is bromide. You can write with this one. Simple to write this particular next type. Ma4BC type. BC type. Now, one is Cl, the other one is what? Br. Two different ligands. Same complex I change. Same complex, instead of writing entire complex, I make this. One is cis, one is trans. Simply changing this particular one of the ligand. So, two chloroligands are there here. Here I write bromide, then here I write bromide. You can simply say these two are again geometrical isomers to each other. One is cis complex, the other one is what? A trans complex. So, Ma4B2, Ma4BC. Next let us see Ma3B3. Three are of one type, remaining three are of one type. How to write this particular geometrical isomers for that type? Now, next one, Ma3B3 plus or minus n, three ligands of one type, like this. Then write for these two, this particular complex, cis and trans. So look here how I write cis and trans. Same, for the same complex I am making it cis and trans. Cl, Cl and Cl. The three I have put one side, or you see, this is actually occupying one of the face of the octahedron. One of the face of the octahedron. Next, this trans complex, this is Cl, I am writing like this. Here you see cis and trans, this is cis, this is trans. Now, this particular cis complex, we also call it as facial isomer. Remember, Ma3B3, the cis isomer also known as facial isomer. Facial. This particular isomer we call it as what? Meridional isomer. Meridional isomer. Meridional isomer. This is actually three ligands and actually one face of the octahedron. Therefore, we are calling it as what? Facial. How? See, octahedron, Cl and Cl, here you take. This is one of the face of the octahedron. One of the face of the octahedron. Therefore, this is known as what? Facial isomer. The next one, what we call meridional isomer. So, Ma4BC type and Ma4B2, Ma4BC, Ma3B3. Next, we see Ma2B2C2 type. Let us write real example, real complex for this model. See now CO, NH3 taken twice, you take H2O taken twice, Cl2. plus, Cl2 plus. For this, theoretically we can write 5 isomers. 5 isomers are possible theoretically. But only out of 5 isomers, only 3 are practically isolated. Whatever it may be, what are the possible 5 isomers? Let me show on the board. Now, first one, cis I write. Look here, Cl cis, aqua ligands, cis to each other, Next, amines, cis to each other. This is what cis. One more, trans we write. Cl I am putting trans. In this particular complex, what I do is everything, all the pairs I write trans to each other. Here all cis to each other. Cis to each other, cis to each other, cis to each other. Chlorides, trans. Amines also put trans to each other. And aqua ligands also I am writing trans to each other. This is cis, that is trans. Cis and trans. One is cis, one is trans. But what I said, theoretically 5 isomers are possible. Now next, these are the 2. Next, third one I write here, see. Each pair I take trans to each other, see, Cl. The remaining NH3, NH3, aqua ligand. This is one. Third possible structure. Next, fourth possible structure. Theoretically 5 isomers I said. Now I keep amine ligands in the trans. Remaining I will keep cis to each other. Fourth isomer. I said theoretically 5 are possible. See, 2 are cis and trans clearly are written. And third possibility and the fourth possibility. In each possible structure, what I did? The chlorides I put trans, their amines I put trans. Next, what is the option is left? Aqua ligands also I will keep in trans position. That you can say is what the fifth structure. The aqua ligands, the trans position, remaining chloride and amines keeping in cis positions. So like this, 5 isomers are possible theoretically, but only 3 out of 5, only 3 are isolated. So number of isomers possible for theoretically is what? 5, and isolated, possible isolate isomers are only 3. Next let us see Ma2 BCDE. Next model see Na2 BCDE, Ma2 BCDE. Plus or minus n, take CO, NH3 taken twice, take different ligands again, bromide you take, chloride you take, and iodide, one I write H2O. This 3 negative charges are there, negative ligands. That's enough. You need not put any charge. As such, you can leave this particular complex without any charge. For this again, cis and trans. This particular amine ligands, once we write in cis, the next we write in trans. Look here. Bromide, chloride, iodide, aqua ligand, you write like this. This is what cis and trans. Only I change the position of the amine ligands. I change the position of amine ligands. Once I kept in cis, next I am writing the trans position. Write whatever you like. This is Br, Cl, and iodide, and you take H2. Like this, this is representing cis. This represents trans. One is cis, the other one is what? Trans. Two possibilities. Next, we take the last example. M, A, B, C, D, E, F. All the 6 ligands are different. Let us discuss that one now. M, A, B, C, D, E, F. Plus or minus n. So 6 ligands are different. You will add a platinum complex, C, Br, bromide, chloride, iodide, nitro, can take amine and P1. So this is what Ma, B, C, D, E, F, 6 ligands are different. For this particular Ma, B, C, D, all the 6 ligands are different. Total 15 geometrical isomers are possible. But writing about all the 15 is not that easy. How the 15 are possible? Out of this particular 15 geometrical isomers, 12 are cis isomers and remaining 3 are trans isomers. Just I show on the board how these are possible, giving rise to 15 isomers. First, we will take one isomer. This is platinum, ClBr take, remaining I, NO2, NH3, P1. Let us consider with respect to Cl and Br, with respect to chloride and bromide, with respect to chlorine and bromine, that is what cis. The next complex, chloride and bromide, we write in trans. With respect to chloride and bromide, this is trans we say. Now, second complex you can write. With respect to chloride and bromide only we are talking about. Cl and Br I put in trans. Then remaining iodine, iodide, nitro, amine and Py take. This is cis with respect to chloride and bromide. This is trans with respect to chloride and bromide. But what I said, total number of isomers possible are geometrical isomers 15. Now I will show the numbering of this particular Ma, B, C, D, E, F type. See now. CO, instead of taking TO, CO, let me take a model complex M. You take 1, 2, 3, 4, 5. This is the sixth position to take. These are the positions on octahedral geometry. 6 ligands, 6 positions. Now, possible cis isomers you see. Possible cis isomers. Now, this you can take 1 2 1 2 6 and 1 3 6 1 2 6 1 3 6 3 4 6 or 1 4 you take 1 4 6 1 5 6. 6 possibilities we write like this: 1 2 6 1 3 1 4 1 5. Next, if you are taking similarly this 2 3, you can also write 2 3 6 and 3 4 6 3 4 6 4 5 6 5 2 6 we write 2 3 3 4 and 5 2 2 3 3 4 and 4 5 5 2. Next, if you talk about 6 6 2 6 6 2 6 3 6 2 6 3 6 4 6 4 6 5 6 4 6 5. All these 12 possibilities coming to be what are all cis. These are all we can consider as what are cis possibilities. 12 isomers now. Next, trans I said 4 or only 3. This is about 12 plus 3, that is 15. So 12 isomers, cis isomers, trans coming to be only 3 isomers trans. Trans. This is 1 6. 1 6 trans. Next 2 4 trans. Next 3 5 trans. 3 5 trans. Like this, total 15 isomers. These 15 isomers, these are possible 12 cis isomers and 3 trans isomers, MA, B, C, D, E, F, exhibiting a total of 15 geometrical isomers. One point you have to remember, all these 15 geometrical isomers are unsymmetric isomers. This point again we will get in the discussion of optical isomerism. Remember, MA, B, C, D, E, F, 15 isomers are possible. All the possible 15 geometrical isomers are unsymmetric isomers, because you cannot cut into equal half any one of this particular isomer. See, we have discussed only monodentate octal geometry with monodentate ligands. Let us see now bidentate and monodentate ligand both are present in a complex. How isomerism is possible? Now, this is only monodentate ligands we have discussed. Now with bidentate and monodentate. Octahedral geometry, octahedral with bidentate and monodentate ligands. Bidentate and monodentate. Octahedral geometry, octahedral with bidentate and monodentate ligands. Let us see the types under this. MAA taken twice, B2. MAA taken twice, B2 plus or minus N. Next, similarly, MAA taken twice, BC you take, B2 or BC you take, two different types of monodentate, B2, BC. Next you can take MAA, B2C2, MAA, B2C2 plus or minus N. Not only symmetric bidentate, we can also write a complex with unsymmetric bidentate. So, here it may be MAA type or it may be MAB type. MAB taken twice, B2 plus or minus N. MAB taken twice, BC. AB taken twice, BC plus or minus N. Like this, we can write these are the possible isomers, possible complexes. All these are exhibiting geometric isomerism. Let us see one by one how they are exhibiting this particular cis and trans isomerism. How can they exhibit in cis structure and trans structure? Let me take the first one, MAA taken twice B2. Plus or minus. See, take the real example, CO, En taken twice, Cl2, plus. How we write this particular, for this particular complex, cis and trans structure? Look here. Take CO, Cl I am putting the cis positions adjacent, and I am writing two ethylene amines, NH2, CH2, CH2 and NH2. Next one, two ethylene amines, this we can take as what? Cis complex. Next we write chloride ligands on axial positions, we can make it what? Trans. One more complex, this we can take as what? Trans. Cis and trans. This is what? MAA taken twice B2. Similarly, we can also write cis and trans structures or geometric isomers. BC type. Let us take one, instead of taking two ligands similar type, similar, now we take two different ligands. MAA taken twice BC type. MAA taken twice BC. Say an example for this, CO, En taken twice, take Cl and Br. Cl and Br. At the place of Cl, same complexes, same geometry. I am not changing total geometry of the complex. I am not rewriting. Same thing. In the place of Cl, keep one Br, ClBr and ClBr. We can make it now geometric isomers. Cis and trans. So this is what? MAA taken twice B2 and again MAA taken twice BC type. Next we see only one bidentate. Only one bidentate and four are this monodentate ligands. Next type. Look here, MAA B2 C2. Take one bidentate ligand, right? COEN. Let me say two aqua ligands, two chloro ligands. Then this is the complex. How to write this particular complex geometric isomers? Let us see now. CO take H2O, aqua ligand and chloride, one ethylene diaminarate. Take this as cis2. This is what let us consider as cis complex. Now either chloride ligands or aqua ligand we keep in the trans position axial. We write the trans isomer. take either chloroligand or aqualigand, right? Then this is what Cl. Cis and trans. Here both aqualigands are cis to each other. Both aqualigands and again chloroligands both are actually cis to each other. Therefore, we are considering it as cis. But here you cannot say this cis. Chlorides are cis, we agree. But here both the pairs are cis to each other. Therefore, we are calling it as cis. But one of the pair is trans to each other. Therefore, we are calling it what? Trans. One is cis isomer, the other one is what? Trans isomer. One is cis, the other one is what? Trans. So, this is the octahedral geometry with the bidentate and monodentate. In some cases, we also observe there are two different types of bidentate ligand, two different types of bidentate ligands and again monodentate ligands. One more model we see, two different bidentates and monodentate. Octahedral with two different bidentates, two different bidentate and monodentate ligands. Monodentate ligands. Two different bidentate and monodentate ligands in this. Let us see in this. Let us write a model first, MAA and BB, two different, and let us see C2 plus or minus N. Now let us the real example on this particular MAA BB, two different bidentates. Look here, CO, one you take PN, the other you take EN, PN and EN are right, and you take Cl2. PN, EN, this one. For this you can write again cis and trans. Look here. Let us write chlorides in cis position. One is NH2, NH2. I am showing this is PN. Next one more EN. Two different ligands and two chloride ligands. Now we make it chloride ligands again in the trans position, that is we write in the axial position, that will be representing trans. Let me write this as cis. Next, trans. One is PN, the next one is what? EN. CH2, CH2, NH2. Say it is trans. See, one is cis, one is trans. So, with two different bidentate ligands. The different models under octahedral geometry with only monodentate ligands, bidentate and monodentate ligands, two different bidentates and again monodentates. But in some cases, we also see that only bidentate ligands also there. Next, in octahedral geometry, with only bidentate ligands, we will see it. Octahedral with only bidentate. With only bidentate. Only bidentate. Look here in this. only bidentate. With symmetric bidentate, there is no geometrical isomerism. What do you understand by symmetric bidentate? Any ligand which is carrying the identical donor atoms that we can consider as what symmetric bidentate. Such ligand is there, then that cannot exhibit geometrical isomerism. Look here, I am writing the same point here. With symmetric bidentate ligands, no geometrical isomerism. The symmetric bidentate ligands, no geometrical isomerism. What is that? Let me give a model complex. Now take MAA taken thrice plus or minus N. See, symmetric means what I said, both the donor atoms are same. Such ligand we consider what symmetric. Then such ligands are there in the octahedral geometry, that particular complex cannot exhibit geometrical isomerism. Let me write a real example. COEN taken thrice. COEN taken thrice plus 3 you take. Right, for this no geometrical isomerism. Then which will exhibit geometrical isomerism? With only bidentate. Wherever unsymmetric ligand is there. What do you understand by unsymmetric? Yes, donor atoms are different. Once for a bidentate ligand, donor atoms are different, then that particular ligand is there in the octahedral geometry, that particular complex can exhibit geometrical isomerism. Let us see what is actually we can consider. Next point I am writing here. With unsymmetric bidentate ligands, with unsymmetric bidentate ligands. Ligands exhibit geometrical isomerism. With unsymmetric bidentate. So what example you can write here? AB taken thrice to take. AB stands for two different bidentates. AB stands for the ligand which is carrying two different donor atoms. Here it is carrying identical donor atoms. It is carrying what? Two different donor atoms. What example you can write for this? See, you can write nickel glycinato plus 1, this particular complex. You know, it is ethylene diamine carrying ethylene diamine, two donor atoms are same. It is actually NN donor. But in the case of glycinato, recollect what is the structure of glycinato. It is NO donor. It is carrying identical donor atoms. It is carrying what? Different donor atom. Such complex only can exhibit this geometrical isomerism. Let me show for this particular complex how it is exhibiting geometrical isomerism. Ni, this complex I am writing, look carefully how it is exhibiting geometrical isomerism. Next one, I write identical donor atoms in the XL position. Then that will be considered what? Cis. Now, next, cis isomer. Next we can write a trans isomer. Keep the different donor atom. Then you can write the trans. Then you can write the trans. This part I am removing. Write this you are taken as a cis. Trans geometry I am showing on the board. Two different donor atoms we write the Excel position. See, identical donor atoms, but it is cis. Different donor atom, that is trans. This should take as trans. One is cis, the other one is what? Trans. So like this, a octal geometry may carry all the three bidentate ligands. All the three bidentate ligands are symmetric, carrying the same donor atoms. Such complex cannot exhibit geometrical isomerism. Like this, a bidentate ligand is carrying two different donor atoms, NO donor atom you take, like glycine. If that particular ligand, bidentate ligand with two different donor atoms is there in the octahedral geometry, then that particular complex exhibits geometrical isomerism. So different types we have discussed here. What are all? Monodentate ligands and monodentate bidentate ligands, and two bidentates and monodentate ligands, and only bidentate ligands are there. How they can exhibit geometrical isomerism? Different types we have clearly discussed it. Optical isomerism. Look here, the complex compounds are having same chemical formulae, Same chemical formulae. Same chemical formulae, which are having same physical and chemical properties. You look here, same physical and chemical properties, same physical and chemical properties, and which differ in their optical properties. Which differ in their optical properties, that means which are differing in their property towards the plane of polarized light, which are differing in their optical properties, which are having same chemical formulae, same physical and chemical properties. Recollect, suppose you talk about geometrical isomers, geometrical isomerism. The complex compounds are having same chemical formulae, which differ in their physical and chemical properties. Geometrical isomers differ in their physical and chemical properties. But what I am saying here, same chemical formulae, same physical and chemical properties, which differ in their optical properties, That means differ in their property towards plane of polarized light, So having same chemical formulae, same physical and chemical properties, which are differing in their optical properties, means which are differing in their property towards plane of polarized light. What do you understand by this? X complex and Y complex, or X geometry, Y geometry you take, X and Y complexes to take. That means one of the X complex and one of the Y complex. X complex reflects the plane of polarized light to right hand side. The Y complex reflects the plane of polarized light to left hand side. One which is actually reflecting toward the right hand side, that is well known to you, that is what we call as dextrorotatory D-isomer, we say. D-isomer. Which reflects to left, we call it what? L-isomer. One is D-isomer, the other one is L-isomer. So these are having all same property, same formulae, same physical and chemical properties, only they are differing in their property towards the plane of polarized light, or you say optical properties. Such complexes are known as what? Optical isomers, and the phenomenon optical isomerism. Next, let us come to the next point. Let us consider coordination number 4 and coordination number 6. Take the coordination number 4, coordination number 4. Let's recollect, in coordination number 4, two geometries are possible again. One is tetrahedral, second one is what? square planar. Coordinate number 4, one is tetrahedral geometry, second one is what? Square planar. One is tetrahedral, second one is square planar. Next, here in coordinate number 4, optical geometry, optical isomerism we talk about. Tetrahedral geometries only exhibit, in coordinate number 4, tetrahedral geometries only exhibit optical isomerism, but not square planar. How can you say this? In any geometry which obeys this three symmetry elements, any geometry which is having three symmetry elements, one is axis of symmetry, center of symmetry, plane of symmetry. Axis of symmetry, center of symmetry, plane of symmetry. I write on the board to see. Any geometry which possesses three symmetry elements, right? Plane of symmetry, second one, axis of symmetry, third one, center of symmetry. Any geometry which possesses three symmetry elements, plane of symmetry, axis of symmetry, and center of symmetry, such geometries are generally found to be optically inactive. Now, consider the square planar geometry. Square planar geometry possesses all the three symmetry elements: plane of symmetry, axis of symmetry, center of symmetry. Therefore, square planar geometries are found to be optically inactive. Imagine a plane, then it cannot give a perfect mirror image. Therefore, the square planar geometries cannot exhibit optical isomerism. Coming to this particular tetrahedral geometries are lacking all the three symmetry elements. Tetrahedral geometries lacking all the three symmetry elements, they are not possessing either of these particular symmetry elements. Take plane of symmetry, center of symmetry, and axis of symmetry. Therefore, tetrahedral geometries only found to be optically active. So, what we can conclude, under coordinate number 4, tetrahedral geometries are optically active but not square planar. So, under coordinate number 4, we take tetrahedral geometry. Under tetrahedral geometry, we discuss different models now. Right, coordinate number 4, tetrahedral geometry. Coordinate number 4, tetrahedral geometry. Under this types, let us consider first one, with only monodendritic ligands, take M, A, B, C, D. MABCD plus or minus N. In this particular MABCD, tetrahedral geometry with 4 different ligands. Very few examples are there. One example I write on the board. Now, very rarely this particular complex are there in the textbooks or any book. 1 or 2 examples are there. Arsenic, take methyl, and you consider ethyl, a sulfide ligand, and C6H5COO also there. This particular complex, arsenic is what? Plus 3. Arsenic is plus 3. 1, 2, 3, 4, 5. This is coming to be minus 2. This is the complex which is carrying over C. All the 4 ligands are different, and the geometry around this particular arsenic coming to be tetrahedral. Now, for this particular complex, I will show the optical isomers. For the model only I am showing on the board. Let's you take simply a tetrahedral geometry A, B, C, D. Take this as what? D isomer. Put a mirror plane. This represents the mirror plane. Then take the L isomer. This one. A, B, C, D. A, B, C, D. One is what D isomer. The second one is what L isomer. Let me write this particular. This is what now C. One is D you say, then other one it is L isomer. One is D isomer, the other one is what L isomer. This is tetrahedral geometry with only monodentate ligands. In tetrahedral geometry with bidentate ligands, you see tetrahedral geometry with bidentate ligands. Tetrahedral geometry with a bidentate. Tetrahedral geometry you take with bidentate ligands. One point here is important in tetrahedral geometry with only structurally unsymmetric bidentate ligands only exhibit optical isomerism. With structurally bidentate ligands, structurally bidentate ligands. What are these structurally bidentate? Take examples. You take one is benzoyl ostanato. Benzoyl ostanato. Benzoyl acetonato. What is this? C6H5 COCH3 benzoyl ostanato. What I said, this is structurally unsymmetric. There I have to mention the word structurally unsymmetric bidentate. Structurally unsymmetric, you write. Unsymmetric bidentate. Structurally unsymmetric bidentate ligands. One is benzoyl ostanato. Second one, let me write salicyl aldehydato. Salicyl aldehydato. Salicyl aldehydato, you know well, simply you write salicyl aldehyde. So, in what way this you can consider as structurally unsymmetric? See, suppose you are making into two equal halves. It cannot be cut into two equal halves. One is benzyl, the other is what? Acetyl. Similarly, you want to take two equal halves, this particular also cannot be cut into two equal halves. Therefore, by donor atoms they may be symmetric. Both are having identical donor atoms. But structurally you talk about, they are not structurally symmetric. So, these two are structurally unsymmetric. What is structurally symmetric ligand? I will show one. Look here. CH3CO, CH, CO, CH, COCH3. This is actually two acyl groups are there. Therefore, structurally symmetric we can consider. But that is structurally symmetric. These two are structurally unsymmetric. Wherever these particular two ligands are there in a complex, wherever these are forming complexes with, consider either zinc plus 2 or beryllium plus 2 or boron plus 3, All these complexes are found to be tetrahedral complexes. Those tetrahedral complexes are found to be optically active. What I said, with this particular two ligands, benzyl ostanato you take or salicyl aldehydato, whenever they interact with this particular zinc plus 2, beryllium plus 2, boron plus 3, forming tetrahedral complexes, those tetrahedral complexes are found to be optically active. Let us take both these examples, how they are forming a tetrahedral complex, how they are optically active. Right. I'll write a complex, you see, base benzyl acetonato, base benzyl acetonato, boron 3, ion you take. Base benzyl acetonato, boron 3. Now, I am writing the formula, see, C6, H5CO, CHCO, CH3 taken twice, boron. This is the complex with a plus charge over it. This particular complex will make it tetrahedral geometry, and I will show how this particular is optically active. A little typical to write, but I will show on the board clearly how it is optically active. Look the board. First to make tetrahedral geometry, tetrahedral, this linkage of this particular ligand, single bond, a double bond, CH, then C double bond 4. One is C6 H5, let me write. The other one CH3. One benzyl. Next, one more I will link here. Look here. Then it is C double bond, CH single bond, and double bond. Let me see. This is what C6 H5. This is what CH3. Let us consider this particular complex as a D isomer. D isomer. Next one, the mirror image of this, let us write and see. Mirror image of this, we will write L isomer. Same, reflect this particular and write the mirror image for this. Now, this is reflecting here. See, I am writing the same that side. CH double bond, single bond, then it is C double bond O, then it is CH3, it is C6 H5. 1. This one, it is now C single bond, CH double bond, single, doubly bonded, and CH3, it is CH3, and this one is what C6 H5. Then you can write this is D, then you can say this is what L isomer, D isomer and L isomer. Next, one more also we written now, this particular salicyl aldehyde A2. Salicyl aldehyde A2. One more complex I will show tetrahedral geometry, how that is again optically active. Now, the next one, base salicyl aldehyde A2, salicyl aldehyde A2, beryllium 2, base salicyl aldehyde A2, beryllium 2. Simply we write the formula. For writing salicyl aldehyde A2, complete name of this ligand we write generally salicyl aldehyde A2, base and beryllium. This is the complex. Now, this is also tetrahedral and that is also optically active we said. Let us see how it is optically active. First to make again a tetrahedral geometry. Tetrahedral. This one. 2 salicyl aldehyde atom. Yes. One of the ligand I am writing C. CH double bond over it. Next, this one. One more I am linking here. 2 ligands. Consider this particular complex as D isomer. So what I say, D isomer. D isomer. Let us see now a mirror plane. Mirror image for this you have to write one more. L isomer. See here, look here. Let us make it here clearly the tetrahedral geometry. Now, this is reflecting here, this is reflecting. Carefully how to write this one. This is reflecting here. Look here. Double bond O and this one. See. Also that this is what D isomer. The next mirror image you can say L isomer. D isomer and it is now L isomer. One is D, one is L. So this particular 2 complexes, one is bis benzyl astaneto boron 3 and bis salicyl aldehyde beryllium 2. These 2 are tetrahedral complexes. They are found to be optically active. Next we see this particular optical isomerism in octahedral geometry. Optical isomerism in octahedral geometries. This we have discussed only in coordinates number 4. Next we see coordinates number 6. That is what? Octahedral geometry.